Welcome. This video is going to look at practice questions 10 on from the Brown SL Chemistry book on page 52. So question number 10 wants to know the total atoms in 1 mole of this compound C6H5CONH2. So first thing I would do is count up the total atoms in the compound, and I see that if I have 1 mole of the compound, I'm just going to write CPD instead of that whole name, I see that there's 7 hydrogen per 1 molecule of the compound. So we're really talking about 7 moles of hydrogen atoms. So then 7 moles of anything, you're just going to multiply by the 6.02 times 10 to the 23rd. So we're talking about 42 times 10 to the 23rd, or 4.2 times 10 to the 24th, which matches with letter D. Question number 11 gives you the following balanced equation, and they want to know how many moles of H2O you could expect if you had 10 moles of each of the reactants. So this is really a limiting reactant problem. If you look at the way the book solves it, I think my way is a little easier, at least it is for me. What I would do is I'd take the 10 moles of the C2H3Cl and see how many moles of H2O I can make. And I see that's a 2-to-2 ratio, so that would give me 10 moles of H2O. Whereas with the O2, 10 moles of O2 is in a 2-to-5 ratio, H2O to O2. So this is only going to give me 4 moles of H2O. So producing the lesser amount makes O2 my limiting reactant, and then A would be the correct answer. Only 4 moles of H2O should be expected to form. Number 12 talks about mixing 2 different amounts and 2 different strengths of NaCl together, and they want to know what the resulting solution will be. Well, the resulting volume is just going to be 10 plus 30, or 40 centimeters cubed. Or we can think of this as 0.040 decimeters cubed. The molar amount, which we'll need to get the strength, is a little bit trickier. I'm going to have to take 0.010 times the 0.20 moles per decimeter cubed, and I see that I'm going to have so this is 0.002 moles, and then same thing over here, I've got 0.0300 decimeters cubed times the strength of 0.600 moles per decimeter cubed. So when I go ahead and punch this in, I come up with 0.018 moles. So just like I added my volumes together, I can add my moles together because these moles aren't going to go anywhere. So it's going to be a total of 0.020 moles, a total volume of 0.040 decimeters cubed. So moles per decimeters cubed is how we find our molarity. And I see I have a molarity of 0.05 moles per decimeter cubed, which matches with letter C. Number 13 says you have an unknown compound with 60 grams per mole as its relative molar mass, but they find specifically that it's got 12 grams of carbon, 2 grams of hydrogen, and 16 grams of oxygen. So this one's pretty easy to approximate because this is about 1 mole of carbon. It's about 2 moles of hydrogen, and it's about 1 mole of oxygen. So we can assume the empirical formula is CH2O, and that gives us an empirical molar mass of 14 plus 16 of 30. So if the known molecular mass is twice that much, or 60 over 30, then I can assume that I just need to double this empirical formula, and the molecular formula must be C2H4O2, or that matches with letter D. So number 14 tells you add 300 cc's of water to a solution of 200 cc's of 0.5 molar sodium chloride. What's the new concentration? Well, my new volume is pretty easy to come up with. That's going to be 500 centimeters cubed, or half a liter, so 0.500 decimeters cubed. My moles are only coming from the second solution, the aqueous solution of NaCl, so 0.200 decimeters cubed times 0.5 molar NaCl means I had 0.1 moles of NaCl in there. So I now have 0.1 moles in 0.500 decimeters cubed, or liters, which means I have a 0.2 molar solution, or letter C. Number 15 wants to know the approximate molar mass of MgSO4.7H2O. And remember, this just means I've got an ionic crystal, magnesium sulfate, that's able to trap water in it. And in fact, one crystal, or one formula unit of magnesium sulfate, can trap 7 water crystals. So an approximate molar mass, you got about 24.3, or 24 for magnesium, 32 for sulfur, 4 times 16 for oxygen. And if you remember that water is 18.02, that's great. Otherwise, 14 times about 1 for the hydrogen, 7 times the 16 for the oxygen. You can punch this into your calculator quick, or you can round even more to 25, 30, 60, 14, and in the 7 times 16, I'd maybe just take 7 times 15, 105. And you're going to come up in that 240 range, and the only answer close to this is letter D, which I believe was 246. Number 16 wants to know which formula is both an empirical and a molecular formula. Since the molecular formula is the simplest formula, it has to be one that can't be further simplified. Well, A can't be further simplified, but B, you can divide each subscript by 5 and reduce to CH2. C, you can divide each subscript by 4 and reduce to CH2. And D, you can divide each by 2 and reduce to C2H5. So the only one that would fit would be A. Number 17 is describing how an air bag works. And they give you a data table. And question A simply wants to know the number of sig figs for each measurement. So temperature, all 4 of those are significant. Mass, only these 3 are significant because the first 2 zeros are just placeholders. And then for pressure, again, all 3 are significant figures. In part B, they want to know the amount in moles of sodium azide present, and they said you have 0.0650 kilograms. So if I change this to grams, this is really 65 grams, and then if I find the molar mass, sodium's 23 plus the 3 nitrogen, my molar mass is just over 65, 65.03. So we're talking right about 1 mole of NaN3. Part C, they want to know how much N2 could you produce. So now I've got to take my 1 mole of NaN3 and look at my molar ratio for the balanced equation. And the balanced equation shows me I get 3 moles of N2 for every 2 moles of NaN3. So that means it's really going to be 1.5 moles of N2. And then they wanted that as a volume. So under these conditions, I can use PV equals nRT. So let me create a little space here. So I'm going to go ahead and shift my P over to the other side, since that's where it's going to end up. It's really V equals nRT over P. So N is 1.5. My R value is going to be 0.0821, one of the rare times they gave me atmospheres. Temperature I have to change to 298 Kelvin, and then I need to divide by the pressure of 1.08 atmospheres. And for volume then, I'm coming up with 34.1 decimeters cubed.